EC 201, lecture 18. Today we are trying to derive a circuit which is basically a current controlled voltage source, and the first idea we had was what? You take the current, you want to convert I into an output voltage which is R times I. What are the problems with this? It has two problems. First, you want an ideal current controlled voltage source to have zero input impedance and zero output impedance. Here neither of them is true. Z in is equal to R and Z out is also equal to R. Then somebody said, hey, how about this? We already know how to make a unity gain amplifier, and since the operational amplifier as we know it is a voltage controlled voltage source, the gain of the operational DC gain of the operational amplifier is infinite, which means that this voltage will be I in R, which will also be equal to this voltage. And now what are the problems with this? Zn is equal to R, which is still a problem. However, Z out is equal to 0. Why? Because the operational amplifier is a voltage controlled voltage source. I mean, since you are tapping off your output voltage from a voltage source, by construction the output impedance is 0. Does it make sense? So what would you do if you want to make Zn equal to 0 and Z out equal to 0? We seem to have solved the problem with output impedance. So the output impedance problem can be solved if the output of this block is taken from a voltage source. Alright? So by the same, however, we are not able to solve the input impedance problem. What do you think if the input impedance of this black box that you are trying to build has to be 0, alright, as it should be for an ideal current controlled voltage source? What do you think that current should, where do you think that current should flow into? If you have a current source like this, if you want the input impedance, alright, and this is your voltage V out. If you want the impedance looking in here to be 0, where must the current flow? Impedance is 0 means what? It's a short circuit to ground. Does that make sense? So conceptually, if this current flowed into ground, then by definition the input impedance looking into whatever box you have is 0. So now imagine you are in a lab and I gave you a current source In. I wanted you to produce a voltage which is In times R. What would you do? I want V out is In times R. Based on our discussion with the output impedance being 0, can you comment on what I might need? What all would you need? You think? Somehow we need a resistor R, right? What else? A resistor in series with the current source is out of question because we know that the input impedance is not going to be 0. Whatever we do, the current source must go into ground. So what? Conceptually, what would you do? What does this mean? It means V out is I in R, which is also equivalent to saying V out by R is equal to I in. Now, does this ring a bell somewhere? So you're in the lab, I gave you a current In, I want you to produce a voltage V out which is dependent on this current. So obviously it doesn't make sense to have a fixed voltage source, because a fixed voltage source cannot change, but you want the voltage to be dependent on this current. So if I had a variable voltage source, how would I be able to make that voltage source equal to In times R? Now you have a variable voltage source. You want to make that variable voltage source, it has a knob on it, you want to turn the knob to make that variable voltage source output to be equal to In times R. So what I would do would be the following. I'll put an ammeter here. I have a variable voltage source, and what would I do? You compare the variable voltage source with In times R, okay? But if you want to generate In times R, you have to pass In through R, which is not allowed, because the moment you pass In through R, the looking in impedance for In becomes R. So the alternate thing is to, these two are equivalent statements, right? So I could either compare V out to In times R, or compare In to V out by R. Okay, so great. So what would I do? I would put R here, put an ammeter, and I will compare this ammeter reading to that ammeter reading. If the ammeter A2 reads a value less than that shown by ammeter A1, then I know that V out is too small, I have to increase, crank up V out. If on the other hand ammeter A2 reads, the reading on ammeter A2 is much larger than the reading on ammeter A1, then I must reduce V out. Does it make sense? And this is conceptually what you would try to do. This solves both problems. Please note that the input impedance is 0. What about the output impedance? Where would you take the output? This is my output, and it's coming from a voltage source, so the output impedance is also 0. Conceptually, this is what you're trying to do. And as I kept repeatedly telling you, once you can verbalize or draw a diagram of a concept, you can always build a circuit to do the same thing. In other words, this variable voltage source is dependent on the difference between the readings of this ammeter and that ammeter. Does that make sense? Okay. So in other words, what we need to do is to compare the currents flowing in this branch and In. So let me redraw this in this fashion. So if V out by R was exactly equal to In, then this current will be the same as this current. Okay? In that case, it doesn't make a difference if I have it like this or if I did this. You understand? This is if V out by R was exactly equal to In, this current is In, this current is In, this current is In. Okay? So this potential has to be 0. Okay? So if the two currents are exactly the same, it does not matter whether this ground was there or not. Now, if this current was larger than In, what do you think will happen to the potential of this node? I'm sorry, if V out by R is greater than In, then the potential at X, what will happen to it? Increases. On the other hand, if V out by R is less than In, the potential at X decreases. So instead of having two ammeters, I could do the same thing with 1 voltmeter. If I hook the two up like this, then I realize that by monitoring the potential at node X, if the node potential at X is greater than 0, which means V out is too high, which means I must must reduce V out. On the other hand, if the potential of X is less than 0, it means V out is too low, which means I must increase V out. V out is a voltage source which is controlled by the potential at Vx. And when must you stop reducing V out? When the node potential tends to 0. And you need something which is very, very responsive to the node potential at X. Okay? The moment the node potential of X even goes up by an infinitesimal amount, you must administer a massive kick to this node so that this guy behaves himself and the node potential at X comes back to 0. So in other words, you must compare the potential at node X to 0 and kick this node in the right direction if the node potential at X is not 0. Does this make sense? So now can you help me figure out what the signs on the op-amp must be? If the node potential at X is greater than 0, it means what? V out, the node potential at Y is too much. It must be brought down. So what does it mean? The X must go to the negative terminal of the op-amp. The inverting terminal, the non-inverting terminal of the op-amp must go to ground. You understand? Now if I redraw it in a slightly different way, this is the voltage controlled current source. Please note that if you were given this circuit, you would in a very straightforward manner be able to analyze. So first you can make sure that this is indeed in negative feedback. How do you make sure it's in negative feedback? I say cut some node here, cut the loop, yank this up. If I yank this up, what happens to this node? I yank this up, what happens to this node here? This also goes up. If this goes up, what happens to this node? This goes down. So there is indeed negative feedback. So once you made sure without any uncertainty that there is indeed negative feedback here, the next thing to do is to apply the rules for the ideal op-amp, which are this potential is ground, this potential is and by the rules of the op-amp embedded inside a negative feedback loop, what must be the potential at the inverting terminal of the op-amp? Must be 0, and no current flows into the terminals of the op-amp. So if In is being sucked out of this node, it must flow through R, which means that the output voltage must be In times R. Why is it In times R? The drop across the resistor is In times R. The left end of the resistor is sitting at 0. So the potential at the right end of the resistor must be In times R. And you can see that the input impedance of, it's a current controlled voltage source, okay, with this being In and this being V out. What is the input impedance of this voltage controlled current source? 0. Why? See, for any value of In, this potential is 0. That's because this is real ground. The potential at this node, the inverting terminal of the op-amp, is also 0 for any value of In, because the op-amp is embedded in a negative feedback loop. Because the moment you try and increase In a little bit, momentarily what will happen? If I increase In like this by a small amount, momentarily what will happen? This node potential will decrease, because you are drawing current out of a node. When you yank current out of a node, the node potential goes down. Okay? But the moment this goes down even by an infinitesimally small amount, the op-amp gets very upset and kicks V out. Okay? Thereby bringing this node potential back to. This all happens very, very, very quickly. So in steady state, when you pull out In, this node potential remains 0. So for whatever value of In you pull out, you will find that the node potential at this node is always 0. Current source, it doesn't know anything except the fact that that node potential is always at 0. So as far as the current source is concerned, it is ground. Okay? And because you know what is inside the box, you know that this is not real ground, and this is called a virtual ground. Now you can get a little greedy and say, hey, if this potential is 0 anyway, then I can, why bother with a current source? I could use a lousy current source. If I have In and R1 for that matter, what is the output voltage now? The input impedance of the current controlled voltage source is 0. What does that mean in practice? If you have a fantastic current controlled voltage source, you can drive it with a lousy current source and still get V out being equal to In times R. What is the voltage drop across resistor R1? So this is an example of a lousy current source which has got some finite output impedance R1. Okay. However, because we have a current controlled voltage source which has got a 0 input impedance, we see that it doesn't matter if In has got a poor output impedance. Ideally R1 should be infinity, okay, if you had an ideal current source. But now even if you have a non-ideal current source, you find that it's not a problem anymore, because the voltage drop across R1, which is this chap here, is 0, because this side is the virtual ground of the op-amp. If the voltage drop across R1 is 0, what is the current flowing through R1? Is 0, which means that there is no current flowing through R1, all the In will flow through across R. The output voltage will still be V out, which is equal to In times R. Now, if you have a lousy current source, you can also represent it as, you can actually represent it in the following way, which is you can draw a Thevenin equivalent rather than a Norton equivalent, and instead of calling it In times R, the Thevenin voltage, I will just call it Vn. This is R1 and this is R. So what is V out now? Minus R by R1 times Vn. This is called the inverting amplifier. You can ascertain again that there is negative feedback here. The current flowing here, if there is negative feedback, these two node potentials must be the same, so this must be 0. The current flowing here is going to be Vn by R1. The same current must flow through R, causing a drop Vn times R by R1, and that drop must occur between, which means that the output voltage will be 0 minus the drop across the resistor. So V out must be equal to minus R by R1 times Vn. This whole discussion was just meant to be a background for deriving the last two ways of biasing the transistor so that the current remains independent of the Vt of the device. Okay. And we found two ways of doing it already, and both of them were based on negative feedback. The first one was, this is compare current in the drain with IRF and apply correction at the gate. The second one was some V bias. We know that both of these are based on the same idea. We want to measure the current in the drain in the MOSFET and go and tweak VGS so that the current is what you want. And we realize that there are two ways of measuring current. One is through the drain, one is through the source. So the first example here compares the drain current to the reference current and goes and kicks the gate in the appropriate